we are going to continue. Now, I made a change for of 3 to add that recursively I was supposed to do number 3. And so I did, but I didn't use that language. The 70th term of the sequence 2.4, 2.88, da 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 da, 581,482, 691,778. Well, that is 581,697,000. Where n is equal to 1, 2, all the way 69 to 70, and so on. Will give you that based on the table. Explicitly, as I stated before, there it is, using the explicit formula. Okay, now to answer 4, 5, and 6. So 4, let's take a look at that. What is 4? As you all know, the towns do not have an unlimited amount of space. So a small town can only grow to be so large. There are limits to the growth, and can be modeled by following this recursive rule. The limit of the area to 1,000. So here's the limit. Here's 1,000. Put this in purple. So everywhere in the formula where I see limit, I'm going to put that number. See? Limit. Highlight limit. And I can choose to put the actual number. And R is my growth rate, which is in this case was blue for 20%. So I'll put that R in blue. So, and U sub minus 1 is the previous term. So this reads, the current term is equal to the previous term plus this huge quantity here. Which I'm going to take off. Well, mess that up. So R divided by the limit times the previous term times the difference. So let's see how that works out. Let's add. I'm going to list the spreadsheet again. X or years since. And now the town limited town area. Town area squared kilometers limited. Didn't like it. Limited town area. Limited area. Okay, so that's limited area. Why is it limited? Because it's going to start at, again, 2, but this time we're going to use this formula that they suggest and introduce a limit. So what was the limit? I'm going to put the limit over here. Escape, put limit. Didn't like it. Why not? It's a keyword. Then limit, didn't like that word. Area limit. And it's just 1,000. So right here, put 1,000, because that's going to be our square kilometer limit. So then this can be equal to, it said, let's read that again. It was the previous term let's see, previous term in yellow and the growth rate in blue and the limit in green. Okay, let's see if I can remember this. So previous term plus the limit, the ratio of the limit of the growth rate and the limit. So it's 1 plus this product. So let me pause this momentarily. Okay, so it's the previous term, the quotient of the rates, and the difference, and the sum of the product of three things, and the previous thing. Let's see how that works. So the previous term is B1, and then it's plus, and a ratio of the limit, what was it? The rate over the limit. So the rate was 0.2 by 20% divided by this ratio, which is C1, and times the previous, times the difference of the previous and the limit, which is C1. So let's take a look at that. Look at the difference backwards. C1 minus the previous. That's better. That way it's growing, but not so much. Now, control, click that. Let's see. Oops. Control, click the middle. Let's fill it. How far are we going to go with this? All the way to 70 years? Why not? Oh, something went wrong. Let's pause it and fix it. Okay, so I've changed the formula to the previous term, 2 plus the ratio of the growth rate to the limit times the previous term times the difference of the limit of the growth rate from the limit. And I could fill that and see what happens there. Just as a test, you could do that and see that works. So the parts that are limit, the previous in the sequence is working. Now, if you want to take it an extra step, we could go here and rewrite this as the area of the growth rate is in D1, so replace that with D1. But we need to say D, and then we don't want the number to change, so use the dollar sign, not the G. I said the symbol, number sign, 1 for that. And the 1,000 is located in C1, so that's backspace there, C, dollar sign, 1. And move over to this and delete that, and it's C, dollar sign, 1. That should work as well. And that, to my mind, is what we had before. So memorize this real quick. Let's see if it fills out right for the next couple. No changes. Good. So it's working because D and C1 are constant, and C1's a constant, and the B, the previous term, is not constant because it's constantly the previous term. So again, let's fill. Control click. Let's fill it for 70 years. Instead of the other number, now we have only, it reaches the limit, and it looks like it reached the limit quite a while. Well, yeah, here. So let's take a look at what that looks like by looking at the scatter plot. Here's this scatter plot, and we can change this to the limited town growth area limit. No, not the area limit, not the growth rate, but the limited area. You see, the limited area has that kind of regression. I mean, kind of scatter plot. It's different than the other one. So you can take a look at that menu. And this would be, the regression for this one is a, not logarithmic, but logistic. So you have to go down here to B, not exponential A, but a limited exponential with a limit is this one. Now, what does this mean? Let D is equal to 0 or not? Well, I'm going to go with the first one. And there's that. There's the fit. So, and there is, you see there on the top, you can see on the function regression that that's the limit up there. 0.219 looks like it's the growth rate that we're using. This is like 750. Where'd that number come from? I have to think about that. But you see you have two characteristics. Now you can leave that as A, put these in here and do some algebra and solve for it. We'll do that momentarily. But for now, let's answer the questions we were asked. And what were they? So number 4, calculate the 70-year growth. So we did that. After 70 years, it does fill up. And number 5, use the graphing calculator and sketch the graph as shown. You can see about the graph. And why do you think restricted and unrestricted looks so different? Well, let's take a look. So 4 and 5, C graph, C scatter plot. And you'll see that it's 70 years. You're around here. Take a screenshot of this. Let's see if I can I move this point out of the way? Here it's 70. So the limit is 999. Take a screenshot of that. Turn that in. And basically it's a number divided by this function. This is e to the negative. So if this were 0, this would be 1, and that'd be 2. 1 plus 1 is 2. 2 that is, I believe, the number you started with. And so 1,000 divided by 2 is 500. That should be 0, 2. So um, what does 0, 2 mean, the y-intercept? Well, if again this is 0, e to the 0 is 1, times this is 740, 741. 1,000 divided by 741. So let's go ahead and insert the graph, where I think it's 1,000 divided by, open parentheses, 1 plus, and in this case, we had like 740 or 750, 740 times e, where's the e, whoops, oh my goodness, tab, well anyway, that's from 0 to 70 there, just change the domain in this, negative 10 is fine, and our maximum here was 1,000, so that's 1,000, I'm going to put negative 500 here, 1,000 here. 700. So let's press tab, and we were going to say that was going to be 1,000 divided by parentheses 1 plus 740 times e to the x to the negative the growth rate 0.20, 20%. And that's what's model my data. If I did that correctly, if I remember, oh, I forgot my variable, excuse me, x. So go back in here, put the x. There it is. So this is a logistic curve. And now I do menu, and I can trace, and I can ask, in 70 years, how much area is there? Well, 999 kilometers squared, because it levels off. And tab, and you can put another, whenever you're going to reach 1,000, my limit. Oh, there it is. So this is S until it'll never get there, because in order to get to 1,000, this would have to get to 1. This is basically 1 over 2x. So this goes to infinity, this goes to 0, which this goes to 1. As x goes to infinity, this term goes to 0 plus 1, which is 1,000. It gets there, but never quite gets there, because this is exponential. It reaches 0. So that's the idea of using this kind of model. And that's why it has the shape it has. Now, how about 0? Where does it start? This particular function. Menu, analyze graph, trace, trace all. Now if I do 0, so 135 is where this thing starts, 1.35 is where it's starting, close to 1. And 50 years from now, 167, and so on. And of course, you can go down and see what's going on with your function. Maybe years from now. Right. Click on this, put negative 100, give some space, so you can see the curve. All right, put your function there, label it. So this is called the logistic curve. Take a screenshot of this if you want, turn this in. Okay. Now for 4.5, let's do Control S to save this. 4.4 rates of change of exponential functions.